Chapter 12. Statistics for Categorical Dependent Variables. Proportions and percentages. Categorical responses are those of a nominal or ordinal type, so they might include responses like true or false, yes or no, survived versus diseased, disease present versus no disease present, benign versus malignant, cancer versus no cancer, and so forth. Situations where there are two possible answers. The words proportions and percentages are often used interchangeably. In this video, I may use those two terms interchangeably. But what is the difference between the two terms? A proportion is the relative frequency from a total of 1 and is typically expressed in decimal form. So for example, 1.0 rather than 100%. A percentage is a rate that can exceed 100%. For example, a 400% increase in usage of antidepressants since 1988. In this chapter, we specifically are referring to proportions, but may at times call them percentages and use a percentage sign to represent them. For example, a Pennsylvania hospital has a February 1st, 2012 policy against hiring nicotine users. The policy stems from a 2003 study indicating that smokers have medical bills that exceed non-smokers by $500 to $2,200 annually. It is also supposed that smokers take more frequent breaks during work, reducing productivity. A researcher is interested in measuring the proportion of job applicants who are smokers or nicotine users of any type. The following table contains smoker information on the most recent 10 applications. So the first column that we have is the applicant ID. Then we have a column that lists smokers versus non-smokers and identifies them using the term no versus yes. You might think of this column as being a list of the responses to a survey, because individuals would post responses as yes or no to the question, are you a smoker? Then this third column is a code which lists 0 for those who answered no to the smoker question and 1 for those who answered yes. We have the code so that we can do statistics. We will define X as the number of successes and N as the number of trials. P will represent the proportion of successes or the relative frequency. The sample proportion, or P, is defined as X divided by N. So in this case, we have 2 ones or 2 yeses out of the total number of people who answered the question regarding smokers. So that 2 divided by the total sample size, which is 10, gives us 0.2 or 20%. The proportion is actually a mean. If you think about it, it has the same calculation. If you look at the codes being 1s and 0s, if we take the mean, we're essentially adding up the values and dividing by the count. Well, that's the same thing we did to find this proportion. So if the data are all listed as 1s and 0s, with 1 being considered the nominal success and 0 being considered the nominal failure, then finding a mean of those 10 values is exactly the same as finding the proportion of 1s versus 0s for those same sample values. Because they are the same, the properties of a mean are shared with proportions. The formula for a standard deviation is listed here. But for dichotomous variables, those with only 2 possible responses, 0s and 1s, the formula for the sample standard deviation is simplified greatly. You can see now all we need to know is the proportion in order to find the sample standard deviation. According to the central limit theorem, for large samples, the sampling distribution of the proportion, p, is approximately normal, with a mean of pi and a standard deviation of sigma divided by the square root of n. Pi represents the population proportion and would be the population mean for dichotomous data. The standard deviation of the sampling distribution, you can see, follows the same formula as is used in any kind of numeric data. Here is a histogram of individual responses. You can see those who are listed as non-smokers represented by this tall bar right here. Those who are represented as smokers are listed in this shorter bar right here. However, if you take a proportion of those individuals who are smokers, you get 0.2. If you were to repeat that with several samples of size 10 and take the proportion each time, you could graph all of those sample proportions and they would have a normal distribution. The mean of that normal distribution would be 0.2, which is the mean of the population, also the proportion of the population, and the standard deviation would be equal to the standard deviation of the population divided by the square root of the sample size. Now an important reminder. The t-distribution is used for confidence intervals and hypothesis tests involving means. So in previous chapters where we looked at confidence intervals and hypothesis tests involving means, we used the t-distribution and talked about how that was the most accurate thing to use in those cases. But the normal distribution is used for confidence intervals and hypothesis tests involving proportions. Consequently, in this chapter, we don't use the t-distribution. One of the main reasons for using the normal distribution for confidence intervals and hypothesis tests involving the proportions is that in order for the proportions to have any accuracy, the sample size has to be tremendously large. So a sample of size 10 or 15 that may have worked for situations involving sample means will not work with sample proportions. Why is that? If we look back on the data for the smokers versus non-smokers, we had 2 that were listed as smokers out of the total 10 individuals who completed the survey. Now what I'm saying is that's not a large enough sample. Why? Because think about how drastically the proportion will change for a single person's response. If just one more of those people had responded as smoker instead of non-smoker, that would have changed the proportion from 0.2 all the way up to 0.3. That's a huge change attributed to just one respondent. We don't want one person's response to have a drastic change on our proportions. If we had, say, a sample of size 100 individuals, and one person's response changed from non-smoker to smoker, it would only change the proportion of smokers from 0.2 to 0.21, a very small difference. Because we should be using large sample sizes when we're dealing with proportions, it is safe to use the normal distribution because with large sample sizes, there is very little difference between values in the normal distribution and values in the t-distribution. The basic formula for a 95% confidence interval for pi, which is the population proportion, looks very similar in pattern to that of a confidence interval for a population mean. The limits are found by taking the sample statistic and adding or subtracting a value that is called the margin of error. And the margin of error consists of a value from the table, in this case the z-distribution table or the normal table, and the standard error, which consists of the standard deviation divided by the square root of n. It's the same pattern we used for confidence intervals when looking at means. Because we typically don't know the value of sigma, the population standard deviation, we substitute that sample standard deviation S in its place. And as usual, this is all easily handled by StatCrunch. A study of hospital utilization was conducted to determine the proportion of patients who were smokers versus non-smokers. The study involved a random sample of n equals 58 hospitalized patients. Of the patients interviewed, 33, or a proportion of 0.569, were smokers, and 25, or a proportion of 0.431, were non-smokers. Construct a 95% confidence interval for the actual proportion of hospital utilization among smokers versus non-smokers. One thing that we have to talk about with regard to StatCrunch and the confidence intervals is that it provides you with two different options. The standard or walled method is the method described in this chapter, and it uses this formula right here. The Agresti-Cool method is an approximation that is considered to be more accurate than the standard walled method. To conduct a confidence interval for proportions in StatCrunch, using the sample statistics, we go to Stat, then Proportions, then One Sample with Summary. We list the number of successes out of the total number of observations. The problem indicates there are 33 patients who were interviewed who are smokers out of the total 58 patients who were interviewed. Clicking on Next, we choose confidence intervals, and then we choose the method that we would like to use. Then we select Calculate. So the 95% confidence interval for the proportion of individuals who are smokers, based on the standard walled method, is essentially 0.44 up to 0.7. If we go back and use the other method, we can choose Agresti-Cool and then click on Calculate, and it changes the confidence interval to 0.44 up to 0.69. So there's not a lot of difference between the results given by the two methods for this example. Now let's look at hypothesis tests for population proportions. The possible hypotheses to be tested look very similar to those that we used for testing population means. We have the population proportion, we have an inequality sign, and then we have the hypothesized value. Again, we have equals versus non-equals, we have less than or equals versus greater than, and we have greater than or equals versus less than. The test statistic also has a similar form. We have the sample statistic minus the hypothesized value divided by the standard error. One thing that is notable is the use of pi with a naught next to it. That represents this hypothesized proportion right here. So whatever constant value you put in your null and your alternative hypotheses, that is the value that goes here, here, and here. So if we're testing that the proportion is equal to 0.5, then we would put 0.5 here, here, and here in our equation. Some would ask, why are we using the hypothesized value in the formula rather than using the sample proportion? The reason for that is we want to set this up as if the null hypothesis is true, which is our underlying assumption. And if the null hypothesis is true, then the population proportion is equal to whatever value we put right here. So in the equation, we want to set it up with that same setting. The degrees of freedom are n-1 as they were for the hypothesis test of a population mean. Now let's look at the same example. Researchers are interested in testing the hypothesis that the proportion of hospitalized patients that are smokers versus non-smokers is greater than 0.50. The null and alternative hypotheses become pi less than or equal to 0.50 and pi greater than 0.50. That makes pi naught, our hypothesized value, 0.50. The question may be, how do we come up with these inequality signs? If we look at what the researcher is trying to show, the researcher is trying to show that the proportion is greater than 0.50. Because of this term greater than, we know that the inequality sign greater than has to be included in our hypotheses. Well, if greater than is one of the options, the opposing option would have to be less than or equals. And because the equals always has to go under the null hypothesis, we know that the less than or equals goes here with the null, and the greater than goes with the alternative. Next, we take the formula for the test statistic and we plug in the appropriate values. For p, we have the proportion. For pi naught, we have the hypothesized value of pi, which is 0.50. And we have the sample size of 58. This yields a statistic of 1.05, with degrees of freedom equal to 57. Again, we go back to StatCrunch with these summary values. To conduct the hypothesis test using StatCrunch for proportions, we go to Stat, then Proportions, one sample with summary. We provide the number of successes in the sample, which is 33, out of the total 58. We click on Next. Make sure that we check Hypothesis Test instead of Confidence Interval. Select the null proportion, which is the proportion listed under the null hypothesis. That constant value under the null hypothesis for our test is 0.50, which is the default, so we don't have to change anything. It then asks for the inequality sign under the alternative hypothesis. In this case, we note that it is the greater than sign. We then click on Calculate to see the results. Here we can see the test statistic is 1.05, which is the same as we calculated here manually. The p-value for the test is 0.14. Because it is not less than 0.05, we fail to reject the null hypothesis. There is insufficient evidence to support the position that the actual proportion of hospitalized patients who are smokers is in fact greater than 0.50. Hypothesis tests can be conducted for comparing two proportions. I would assume that comparing two proportions to each other is probably even more often done than comparing a single proportion to a constant value. Here are the different hypotheses that we can test. We can test that the proportions are equal to each other versus not equal, that one is greater than the other, or that one is less than the other. We return to our hospital utilization study. The researcher would now like to know if the proportion of patients who are smokers who were admitted to the hospital last year was different than the proportion of patients who are smokers who were admitted to the hospital the prior year. So we've got two different groups. We've got those who were admitted last year and those who were admitted 2 years ago. And we're looking at the proportion of smokers in each of those groups, and we want to compare those two different proportions to see if they are equal or not equal. Of the 300 patients who were interviewed last year, 91, or 0.303, were smokers. Of the 250 patients who were interviewed the prior year, 78, or 0.312, were smokers. Let's conduct this hypothesis test in StatCrunch. To do this, we go to Stat, Proportions, and now we go to two samples because we're comparing two different proportions and not just one. We go to Summary because we have the summary measures rather than the raw data. Otherwise, we would go to With Data. In the following dialog box, we just enter the values that we have for the two samples. For sample 1, we have 91 out of 300. For sample 2, we have 78 out of 250. We click on Next and make sure that we've checked here that it's a hypothesis test rather than a confidence interval. We indicate the value of the difference between the proportions in the null, which in this case, because we're looking at the proportions being equal, the difference in the proportions is 0. Essentially what this allows us to do is say, I believe that the differences between the proportions is 0.30. And so we can actually look for a specific difference between the proportions if we want to. If we're just looking to see if they're equal versus not equal to each other, then we leave the difference in the proportions as 0. We make sure we select the inequality sign that's in the alternative hypothesis, which in this case is not equals. And then we select Calculate. The results show us that the difference between the two proportions was very, very small. In this case, it was minus 0.00866. We have a test statistic as well, and the resulting p-value is very high. It's a very high value because the difference between the two sample proportions was very, very low. Because the p-value is greater than 0.05, we fail to reject the null hypothesis and conclude that there is insufficient evidence to support the position that the proportions of smokers between the two different years is different. Previously, we looked at hypothesis tests and confidence intervals for 1 and 2 proportions using the normal distribution. But what if we have more than 2 proportions to compare? The chi-square goodness of fit test compares 2 series of multiple proportions each. Let's look at an example. One day each year, the local college holds a day of community service in which all the students are supposed to do activities to support the community. Activity organizers had hoped that participation would equally represent freshmen, sophomores, juniors, and seniors. A random sample of 300 students is selected, and it is found that 95 are freshmen, 85 are sophomores, 70 are juniors, and 50 are seniors. At alpha equals 0.05, which is our significance level, test that there are an unequal number for each classification. Now looking at the values, 95 freshmen, 85 sophomores, and so forth, it already looks like there's a difference between the numbers for each of the classifications. But remember, we're looking at a test that will compare the differences for the population proportions and the population totals, not just the sample values, because we've just collected a sample of 300 students, but we could easily have collected a different sample of 300 students and come up with very different numbers. And so we're conducting the test because we want to show that there's a significant departure from equality among those different classifications. So do the frequencies 95, 85, 70, and 50 differ significantly from 75, 75, 75, and 75, which would represent equal representation for each of the classifications? Where does the 75 come from? It comes from taking our total of 300 participants and dividing it up by 4 because we have 4 different classifications. If we write it as proportions, we have 95 out of 300 for freshmen, 85 out of 300 for sophomores, 70 out of 300 for juniors, and 50 out of 300 for seniors. Those are our values that we have from our sample. What we would expect from our population is 75 out of 300 for each of those classifications. That would demonstrate that there is an equal proportion for each group. And it doesn't matter that we list 300 as the denominator here for the population, even though that's the sample size, because we're just looking at the proportion, not at the specific totals. So our hypotheses are, is the population proportion for each of these classifications equal, or the alternative is that the distribution, or this series right here, is not as it is stated in the null hypothesis. And there are many ways that that could be the case. It could be that 2 of them are the right proportions, but the other 2 are not, or something, maybe all 4 of them are vastly different from each other. So we just state it like this as opposed to using equals and not equal signs. Now you will note that we have 2 different categories. We have observed and expected. So we have observed, which is what we saw for the totals in the sample, and we have expected, which is what we would have expected the totals for each of the classifications to look like had the null hypothesis been true. So we want to compare the observed values versus the expected values. StatCrunch looks at totals instead of proportions. It calculates the proportions for you, but it expects you to enter the values as the total values instead of as the proportions. So if we want to do this in StatCrunch and we're provided with the proportions instead of the total values for each category, then what we need to do is multiply the sample size by each proportion, and that will tell us the values that we need for expected. There's also another note that these tests are not really accurate if the expected frequencies are less than 5 for any category. So here we have expected 75 and expected 75 and so forth. If we have such a small sample that the expected values are less than 5, then our results are not going to be very accurate. And so you want to make sure that you use that as a check when you're doing these tests to make sure that you have an adequate sample size. Otherwise, you know that the results are not going to be very reliable. The formula for the test statistic for this test looks at a comparison between the observed values and the expected values. So observed sub I represents the observed frequency for one of the categories, and expected sub I represents the expected value for one of the categories. And by categories, I mean freshmen is one category, sophomores is one category, juniors is one, and seniors is one. So the values of observed and expected are these values right here. And essentially what this is just saying is that we're going to take one of the observed values and we're going to subtract the associated expected value. So we're going to go to freshman and we've got a 95 and that's our observed value, and we're going to subtract from it the 75, which is our freshman expected value. Once we've found that difference, then we square it and divide it by the expected value again. So these two values here are the same. We just use it twice in the formula. Once we have done that for freshmen, then we do it for sophomores, then we do it for juniors, and then we do it for seniors, and then we add up all four of the results. This test statistic is compared to a chi-squared distribution probability with degrees of freedom equal to the number of categories minus 1. So again, we look at our example where we have 4 categories, so our degrees of freedom is going to be 4 minus 1, which is 3. We have our observed values for each of the categories and our expected values for each of the categories. So we take freshmen, for example, right here in this first part. We have 95 observed minus 75 expected divided by 75 expected. And then for the second group, we have for sophomores 85 observed, 75 expected divided by 75 expected. Then for juniors, we have 70 observed versus 75 expected. And for seniors, we have 50 observed versus 75 expected. So we do that for each of our groups and we add up the totals. If you notice what's taking place here, we're comparing what we observed to what we expected. And if that difference is 0, that means that what we observed is the same as what we expected. And that means that there's no difference. If the null hypothesis is true, then this test statistic should be very close to 0, meaning that there aren't drastic differences between the values that were observed and what we expected. The value of our test statistic is 15.333, which is not very close to 0. In many cases, the chi-square distribution is a right-skewed distribution. You can see it pictured here with the chi-square calculator from StatCrunch. If we enter the degrees of freedom and our test statistic here, and we change the inequality to a greater than sign so we can see the area in the right tail, then we can find that the probability more extreme than the test statistic that we found, 15, is only 0.00155, which is our p-value and is a very small value. What that indicates is that our differences between observed and expected values was pretty extreme. There were big differences. And because the p-value reflected in that is smaller than 0.05, that indicates that we reject the null hypothesis and conclude that there is sufficient evidence to show that the proportions of participants are not equal for each of the different classifications. There is a more automated way to do this in StatCrunch, and that would be to include a column of data for the observed values, a column of data for the expected values, and then in StatCrunch we go to Stat, Goodness of Fit, Chi-square Test. Under Chi-square Test, it provides us with this window right here where we determine which is the column that holds the observed values, which is the column that holds the expected values. Then we click on Calculate, and it provides us with the output. The output here gives us our chi-squared test statistic automatically and our p-value. And if you look at these two values, they match up with what we found previously. Contingency tables are tables of frequencies that are used often in politics and in social sciences. We're going to look at two different tests that use contingency tables: the independence test and the test of homogeneity of proportions. For example, a marketing official for a retail grocery store is interested in determining if the shelf location is influenced by the brand of product being sold. You may or may not have recognized this, but at the grocery store, product placement is a very important issue, and the products that are placed at eye level in important high traffic areas tend to sell better than those that are harder to find or harder to see. A sample of 1,000 grocery items was classified according to brand type, be it a national brand, a local brand, or a brand that was created by the grocery store chain. And shelf location, which refers to the location of the product on the shelf, whether it be on a top shelf, a middle shelf, or a bottom shelf. The question then that is asked is, does the shelf location depend on the brand type? You could think of a number of reasons for this question being asked. It could be asked by the chain to make sure that the right products are being put in the right location. It could be asked by the producer of the product to understand where their product's being placed on the shelves. And it could be looked at by customer organizations to determine if the national or more expensive products are being put in the ideal locations, or if the chain's own products are being posted in the appropriate location. Or it could be looked at by local government officials to see if the local brand is being pushed away and hidden somewhere on a bottom shelf, as opposed to the other types of brands. So our contingency table here has two different variables. It has one variable which is brand type, national, local, or chain, and it has another variable which is shelf location, top shelf, middle shelf, or bottom shelf. Then each cell in this table, which each number is going to be represented by a column and a row, each of those cells represents the number of products associated with that row and that column. So, for example, this 140 represents national brand products that were located on the top shelf. This 125 over here represents local brand products that were on the middle shelf. And the 165 would be local brand products that are on the bottom shelf, so forth. And then we have row totals, which are a total of these three values. And then we have columns totals, which would be a total of the different column values. The test is then looking at the patterns that are seen in these contingency tables. The test wants to determine if there's a difference. And so, for example, where you've got 350 top shelf, 350 middle shelf, and 300 bottom shelf, you can clearly see that there are fewer products on the bottom shelf than there are on the other two shelves. So if you look at the different brands and they have a higher number on the bottom shelf than they do for the top or middle, then that would be an indication of not a proportional distribution of the products. So for the chain, for example, it follows that pattern. You have your smallest number here on the bottom shelf, which represents what you would expect looking at the totals. For the other two, you don't see that. For the national brand, they don't have hardly anything on the middle shelf. And for the local brand, they don't have hardly anything on the top shelf. So that right there gives us an indication that our test is probably going to be significant. Otherwise, we would expect the patterns to be similar across each brand type. The other way you can look at this is you have more local products than you have national or chain products. So because you have more local products than you have national or chain products, you would expect that for each of the shelves, you would have more local products. So for the bottom shelf, you do. You have 165 versus the other two. For the middle, you have more than the national, but you don't have more than the chain. And then for the top, you have less than you have of either of the other two. So again, the patterns don't match what you would expect. You would expect the local value to be higher for each of the shelves than for the national and the chain for each of the shelves. The formula for the test statistic is the same as what it was for the goodness of fit test. We have observed minus expected squared over expected. So once again, we are looking at what we expected to see and what we actually observed, and we're finding the difference between those two, and we're scaling it. If the null hypothesis is true, those differences should be close to zero, and our test statistic as a total should be close to zero. The observed and expected values are going to be the table cell values. If we look at our contingency table again, we want to find an expected frequency for each of these different cells in the table. The way we do that is using this formula right here. The expected frequency is equal to the row total for that cell times the column total for that cell divided by the grand total for the whole table. So for example, the expected number of national brand products on the top shelf would be found by looking at this cell right here that is in the national column and the top shelf row, and it has a column total of 325 and a row total of 350. So you take that row total times the column total and divide by our grand total, which is 1,000. That gives us a value of 113.75. So we would expect, if the patterns hold based on the row totals and column totals, then there should only be about 113.75 products from the national brand that are on the top shelf. We do that same process for all of the cells, finding expected values for each. So for example, the chain, brand, and the bottom shelf, this cell right here where there's a 30 observed, what we would expect to see, we could find by taking the bottom shelf row total, multiplying it by the chain column total, and dividing by the grand total. So 325 times 300 divided by 1,000. That would tell us what we expect to see in this cell. And we would compare that to the 30 that we actually observed. So this table now includes in parentheses each of the expected values next to each of the observed values. And now let's look at the patterns again. If you look at the row totals, we have more top shelf and middle shelf items than bottom shelf items. So in each case, the expected values are higher in the top and middle shelf than they are in the bottom shelf. Then looking across brand types, we have more local products than we have national or chain products. So looking at each category, you have a higher number for local than you do for national or chain. A higher local number than national or chain, a higher local number than national or chain. So in parentheses, those are the values that follow the patterns expressed by the row and column totals. Outside of the parentheses, we have the actual values that were observed in our sample. And so our test then becomes a comparison of the observed versus the expected. And we do that for every cell in the table. After we've done that for all 9 of those different cells, then we add them all up and we get a total. And here our total is 149, which is far, far away from 0, which would indicate that the null hypothesis is true. So because it is so far away from 0, we're likely going to reject the null hypothesis. Degrees of freedom are found by looking at the number of rows minus 1 and multiplying that by the number of columns minus 1. The degrees of freedom for this example, because we have 3 rows and 3 columns, gives us 2 times 2, which is 4. Now, when you're looking at the degrees of freedom, make sure you're only counting the rows and columns that have the actual data. You don't count the row total or the column total. So if we go back to this contingency table, you can see we have 3 rows that have data, and then we have this 4th row, but this is just the totals. So we don't include that last row or this last column when we're deciding the degrees of freedom. We just have 3 columns, 3 rows. Now, looking up the degrees of freedom of 4 and the test statistic of 149.741 in the chi-square calculator in StatCrunch, we get a p-value that is so small that StatCrunch merely indicates that it is less than 0.0001. Because that is less than 0.05, we reject the null hypothesis and conclude that the shelf location is dependent upon the brand type, meaning that certain brand types have different representation on the shelf locations than other brand types. Now let's look at how we would do this in StatCrunch in the automated way. There are a number of different ways of getting the data into the table, and one of those ways is to have it in a Excel spreadsheet and then just copy the values in the Excel spreadsheet and then go to data and load data from paste, and then you could paste them in. Or you could save them in the Excel spreadsheet and then load them in from that Excel file. The easiest but longest way to do this would be to just type the values in. So what I've done here is I've opened up an Excel spreadsheet and I'm going to type in the values that I have in my contingency table, and then I'm going to transfer those to StatCrunch. So I want to show you the process for doing that. So the first thing I do is I need to have a column for my values here on the left that are essentially my row labels. And so I could say shelf as the name of it, and then we go top, middle, and bottom. And then the next one over we have national, then local, then chain. And we just enter in the numbers as they appear in the contingency table. So 140, 80, 105, 60, 125, and 165. So these are the actual counts from our sample. These aren't the expected values. StatCrunch can actually figure out the expected values for us automatically. So we have 150, 145, and 30. So once I've entered all of my data into Excel, then I can highlight it all and select copy, go over to StatCrunch, now I can't directly paste it into these cells. What I have to do is go to data, load data, from paste, and then here I click in here to get my cursor in there, and then right click and paste. So that's my data from the Excel file that I copied over here. I indicate that the first line is used as the variable names. So shelf, national, local, and chain are the variable names. Tab delimiter is what you choose when you're working with Excel. and you can give it a name if you want. Then you go to load data, and there it is. It puts it there in StatCrunch for you. Now, it may seem that you shouldn't need this first column here because it's just a bunch of labels, but it's actually a required column in StatCrunch if you're going to do the test this way. Then we go to Stat, and we go to Tables and Contingency for Contingency Tables, obviously. Now, although it looks like we have raw data, these data are actually summary values. And so we click on With Summary, and it gives us this dialog box. We then choose the columns for the table, which are the columns that have our numbers in them. Then we select the column that has the row labels, which is shelf right here. And so we go to shelf, and then column variable, which is going to allow us to give a variable name to these three columns right here. And we will just call that brand because they're all the different brand types. But as you saw, it said optional, so you don't have to give a column variable name here if you don't want to. Clicking on Next gives us the options to actually ask for the expected counts. And so I'm going to click on that because I want to see what those counts are. Here we have a Fisher's exact test, which only works for 2x2 tables, and since we have a 3x3 table, it won't work for us. We then click on Calculate, and here are the results. So it lists the observed values, and then below it, it lists the expected values. 113.75 is what we had figured out, and this shortens it to 113.8. But you can see here this contingency table looks very similar to the contingency table that we had. It gives you the chi-squared degrees of freedom, which is 4. It gives you the test statistic value, which is the 149.741 that we had, and it gives us the p-value. So everything that it provides here with the output is what we were expecting to see. And again, based on the p-value, we can reject the null hypothesis and conclude that the shelf location differs depending on the different brand types. So this test was a test of independence, which is looking at the independence between the two categorical variables that are expressed in the contingency table. The two variables in this example are brand, which is the column variable, versus shelf location, which is the row variable. So we only have, even though we have 3 rows and 3 columns, we only have 2 variables. Those 3 columns are represented by the variable brand type, and these 3 rows are represented by the variable shelf location. They're categorical variables, meaning that each of the values is a category, and they all come from one sample. So a sample of 1,000 grocery items was classified. So you can see that although we have rows and columns, these all were just taken from one single sample. And that's key because with the test of independence, you're looking at 2 different variables measured on each individual. So in this case, the individuals were products, and we were looking at the 2 different variables being measured as, was it a national, local, or chain brand, and was it located on the top, middle, or bottom shelf? And so for each product in our sample, we measured those 2 categorical variables. With homogeneity of proportions, we have a different setup. Although we're still looking at contingency tables, the homogeneity of proportions setup is different than that of independence. Here is an example of homogeneity of proportions. Again, we have a contingency table. In this case, a professor is interested in determining if the proportion of elementary education majors is the same for education colleges at several different universities. The question is the proportion of elementary education majors the same for University A, University B, and University C? 3 different samples were collected for this study, one at each of the education colleges for the 3 different universities. So as you can imagine, they went to the College of Education for University A and said, we need to interview 80 of your current students. And so they looked at 80 of the current students and determined whether or not the person was an elementary education major or some other major within that college. We have three different groups or three different samples instead of one sample. That's different from what we had in the previous example where we just had one sample and we had two different categorical variables measured on each individual product in that sample. Here we actually have three samples and we're looking at one categorical variable being measured on each of those three samples. So it's important to note the difference that exists there. So we're not looking at one sample with two variables, we're looking at three samples with one variable. So the three samples with one variable that we have here is going to be used for the homogeneity of proportions test. And what we are trying to find is, are the proportions the same for each of those groups? Now, the nice thing about it is the test for independence and the test for homogeneity of proportions, they're both conducted in the same fashion. They use the same steps. The difference then in the results is how we interpret. But you follow the same steps, so that makes it very nice. We don't have to learn two different sets of steps. So we have the observed values for each of the universities. Those are the values that are not within parentheses. So of the 80 students in University A that were sampled, 60 of them were elementary education majors and 20 of them were other majors within the College of Education. For University B, we had 45 and 35, and for University C, we had 40 and 40. So that's what was actually observed. Then we look at what was expected. If you look at the totals, you can see there are more overall elementary education majors than there are other majors. And so you would expect that for each of these columns, you should have more individuals in the elementary education major than not. And that is true of University A, that's true of University B. University C, there's an equal proportion in each for that sample. And so the idea is we're looking at what we would expect and seeing how these values differ from that. We find the expected frequencies the same way as we did for the test of independence. We take the row total, multiply the column total, and divide by the grand total. So here we have the elementary education majors for University A. We have 60 that were observed, but that's in the first row and the first column. So we look at the row total as 145 and the column total as 80. And we multiply those two values together and divide by 240, which is the grand total. And that will give us the expected frequency for University A elementary education majors. And that gives us 48.33. We do that for each of the cells to get each of these expected cell counts. And then we do our test to compare what was observed to what we expected. Here's the test statistic where we've taken each observed value and subtracted each expected value. And the total for our test statistic is 11.329. And that value is far away from zero, though it's a lot closer than it was in our previous example. So we have to look at our chi-square distribution to see if that value is significant. Using the degrees of freedom method we used before, number of rows minus 1 times number of columns minus 1, we get the number of rows being 2 minus 1 times the number of columns, which is 3 minus 1, gives us 2 as our degrees of freedom. Using that in the test statistic of 11.329 in the chi-square calculator in StatCrunch, we get the p-value as 0.0035. So it's still below the 0.05 level that we would expect if the null hypothesis is true. Consequently, we reject the null hypothesis and conclude that the proportion of elementary education majors differs for the different universities. Now, how would we do that the automatic way in StatCrunch? Again, we can go to Excel and enter the values there and then transfer them over to StatCrunch. So we have major, and I'll just put EE for elementary ed and other for other. And then we have University A, University B, and University C. And the values we have are 60, 20, 45, 35, 40, and 40. We highlight all of these values and copy them. And then we go to StatCrunch, data, load data from paste. Click here in the space and right click. That gives us our values. Select load data, and there they are. Then we would go to Stat, Tables, Contingency, with Summary, select our 3 columns of numbers, select the column that has our row labels, give our columns of data a variable name, click on Next, and if we want to see the expected cell counts, we can choose that and select Calculate. Here's the results. Again, it provides us with the expected cell counts for each of the cells. It gives us the observed cell counts, and it tells us what the degrees of freedom are, the test statistic, and the p-value. And you'll notice that these all match up with what we found previously. In summary, hypothesis tests and confidence intervals for 1 or 2 proportions use the z-distribution, as opposed to the t-distribution for means. There are 3 different chi-square tests: the goodness of fit test, the test of independence, and the test for homogeneity of proportions. For the goodness of fit test, we have a single series of proportions, and the distribution of that series is compared against a series of constant proportions to see if the series or distributions match. Now, by constant proportions, what I mean is we're not comparing these proportions to other sample values. We're comparing them to actual numbers. And so we have a sample that we're comparing to constants. For the test of independence, we have frequencies that consist of individuals from a single group with measures on 2 categorical variables. The test determines whether or not the 2 variables are then independent. For the test of homogeneity of proportions, the individuals come from multiple independent groups, and the test determines whether or not the proportions for each of the groups match up or are the same. And again, we note that a lot of the similarities between the test of independence and the test for homogeneity of proportions, they both seem to be fairly different from the goodness of fit test, but even the goodness of fit test uses the same chi-square distribution, but degrees of freedom are figured out a little bit differently, and we're comparing values not against expected values, but we're comparing them against constants, whereas in these two we're comparing the observed values against expected values. So there are some differences. And that is the end of Chapter 12, Statistics for Categorical Dependent Variables.